No, will you mute? There's a lot of, yeah, thanks. Okay. Okay, so let me start. So, yeah, I just want to start by clarifying a little mistake I made last time, which is that I stated that this kernel of add little I plus identity, this is equal to the span of H. This is not quite correct. So this contains the span of H, but it's not equal to the span of H. So we don't need this actually to determine what is the kernel of add I plus identity. Instead, if we want to show that ni bracket ni bar belongs to this vector space script H, for that we can just use the fact what Utshav pointed out later to me, the well-known fact that if you take the root spaces, then the bracket of G alpha and G beta is contained in G alpha plus beta. Right?
Yes.
This from the Jacobi identity. So here what we have is a bracket of, if I look at bracket of H ni bar, a bracket of H with bracket of ni bar, then I use the Jacobi identity. So that means when I cyclically permute these three, so the next term will be, so this is A, B, C, the next will be B, C, A. So B is ni bracket with B, C, ni bar H, right? Plus BCA, then CAB, right? So ni bar bracket with H bracket ni, right? This is equal to 0, right?
Yes.
Yes.
And this ni bar bracket H, what is this? This is equal to minus alpha I ni bar, right? This we saw last time.
Yes.
Sorry, actually the bracket of H and ni bar is minus alpha I ni bar. So this is going to be plus alpha I ni bar, right? Because the bracket is skew symmetric. And this bracket of H and ni bar, this is going to be alpha I ni. So I get alpha I ni bracket ni bar and alpha I ni bar bracket ni. So these two cancel, right? Okay. So this sum is equal to 0, right? So therefore this term is equal to 0. Yeah. All right. Yes.
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 And now we use the fact that the rank of G is 1. So we're in a rank 1 symmetric space. So in a rank 1 symmetric space, the centralizer of H is just H itself, right? So this implies that ni bar bracket, this belongs to the centralizer of H, which is equal to just H itself, RH itself. All right.
Yes.
Yes, sir.
Okay, so therefore, so this proves that this script H is a subalgebra. Okay. And then the rest of the argument is the same as before. So, so the image of script h under the exponential gives a Lie subgroup, say S, which is isomorphic to SL2R. The rest of the argument is the same as before, right? And then you look at the orbit of the origin under S, and that gives you a two-dimensional submanifold, sigma. And this is a totally geodesic submanifold, right? Because we saw that any 2 points in this submanifold, the geodesic in the whole space joining them lies inside the submanifold, right?
Yes.
Okay. So that's all right, yeah. So in fact, this SO2R that we have here inside this SL2R, the infinitesimal generator of that, actually we can get, what happens is, so let me draw you the picture again, but let me draw it horizontally so that it's easier to see. So you have the AT orbit, and then you have the flow of Ni, which is contained inside a horosphere. Okay, and then so if this is this is the action of e to the s Ni, right? And then the geodesic involution, it maps this horosphere to the opposite horosphere like this. Right? And it conjugates this e to the s Ni to, so this is the geodesic involution I, and it conjugates, so this point will map to this point, and this point will map to this point. So this e to the s Ni will look like this. It'll act like this on this horosphere. So this will be, sorry, e to the s Ni bar. Right? Okay.
Yes.
All right. And AT will act along this geodesic. Okay, so along this geodesic, you'll have e to the th acting here. So this is the picture. Okay. Now, how do I get? So I know that I have a group K of rotations inside here, right? So this is a one parameter subgroup. It's isomorphic to SO2R, which is S1. So this should be e to the, so, oh, yeah, it's just a bad notation. So, so this should be some e to the TKI, right? T and R. A subgroup of S, which is isomorphic to SL2R. Okay. So how do I get these? These act by rotations on this horizontal disk, right? Which is a copy of H2. Now, so if I look at the infinitesimal generator of this Ki, right? This should be a vector field which vanishes at the origin, right? Because the origin is a fixed point of the flow.
Yes.
So how do I get a vector field which vanishes at the origin? Well, what I can do is, if I look at, say Ni is going like this around the horosphere. So at the origin, Ni points like this, right? Okay. And now Ni bar is given by applying the derivative of I to Ni, right? So at the origin, the derivative of I is minus identity. So at the origin, Ni bar will therefore be minus Ni,
Yes.
right? So therefore, if I put Ki to be Ni plus Ni bar, okay, then so this is an element of my Lie subalgebra H. Okay. So then Ki at the origin is 0. Right? So the flow will fix the origin, and it's a flow by isometries. So there will be rotations of this disk. Is this clear?
Yes.
Okay. So this is how you get the rotation component. You get Ni plus Ni bar. In fact, if I identify these with matrices inside SL2R, what happens is that H is identified with a matrix 1, 0, 0, minus 1. Okay. Ni is identified, say, with, say, 0, some xi, 0, 0. Okay, these are all trace 0 matrices, right? Little s, these are in little SL2. So Ni bar will be what? Ni bar will be 0, 0, minus xi 0. Okay, this will be Ni bar. All right. And when I take the sum Ki, which is Ni plus Ni bar, this will be identified with the matrix 0, xi, minus xi, 0. Right? Okay. So this is just a scalar multiple of rotation by 90 degrees, right? The matrix J. Do you understand? So when I take e to the j, I'll get all e to the tj, I'll get all the rotations. Is it clear?
Yes. Yes.
Okay. Yeah, when I take the exponential of h, I'll get the diagonal matrices, e to the t0, e to the minus t. When I take the exponentials of the ni's, I'll get the unipotent matrices 1, s size 0, 1. And here I'll get 1, 0, minus si 1, and so on. All right?
Yes, sir.
Yeah. Is this clear? Okay. So this is the picture. Okay. So now I just want to finish this discussion of symmetric spaces by so yesterday Utsav was asking me about the relation between the roots and the horospheres and the group N. Okay. Oh, maybe I should, yeah, actually, yeah. Okay. So maybe I should make one comment. This add I, what is the kernel of add I plus identity? So if add I of some vector W is equal to minus W, yeah, then what does this mean? This means if I put GT to be the one parameter subgroup e to the TW, right? Then I know that I GT I inverse, right? This is going to be e to the T add I of W, right? Which is e to the minus TW. So this will be G minus T. Is this clear?
Yes.
Okay. Okay. So if now I'm just saying if W is in script G is such that add I of W is minus W, then let GT be e to the TW, then I GT I inverse is G minus T. Okay. Now using this, we can classify what this GT will look like. This group of isometries. So this uses a very general classification of isometries for what are called cat minus 1 spaces. Okay. So I'll just so in the case of a rank 1 symmetric space, it is a negatively curved, simply connected complete manifold. In particular, that implies it is a cat minus 1 space. Okay. And for such spaces, you can define a boundary at infinity in terms of equivalence classes of geodesic rays, right? Like we discussed last semester. Okay. So if G is an isometry of a cat minus 1 space M, then either one fix, if G has a fixed point inside M. Okay. So fix G intersect M is non-empty. Okay. So then we say G is elliptic. So this is like the classification of isometries of H2, right? Otherwise, fixed G is singleton, say xi, which is in boundary M. So there are no fixed points inside. There's just one fixed point on the boundary. So then we say G is parabolic. And finally, the third case is where fixed G is a pair of fixed points, xi plus, xi minus in boundary M. And in this case, G is hyperbolic. Okay, so there are only these three cases which can occur. All right. So for M, a rank 1 symmetric space, and G, where the isometry, the orientation preserving isometry group of M is a semisimple D group G. And then if you take its Cartan decomposition, K, A, N, okay, then in fact, what happens is the elements of K, these are all elliptic. K is in fact the stabilizer of the origin, right? So these are all elliptic. The elements of A, these are all hyperbolic, right? A is, it preserves one geodesic, right? The elements AT. So the endpoints of that geodesic on the boundary, those are the two fixed points xi plus, xi minus, all right? And finally, N, the nilpotent group, the elements of this are all parabolic isometries. Okay. See, the nilpotent group, it preserves horospheres based at a point on the boundary. That point on the boundary is the unique fixed point of these parabolic elements. Is this all right?
Yes, sir.
Yes, sir.
So geometrically, that is what this Iwasawa decomposition is. You can write any isometry as a composition of these Kan. I mean, actually what happens, the Iwasawa decomposition, if you want to see it geometrically, it's very simple. You see, any isometry is determined by its derivative at the origin, right? If I know the image of the origin, say G dot O, and I know the derivative at the origin, then I know the isometry, right? Yes?
Yes.
Okay, now to determine the derivative, it's enough to take an orthonormal frame at the origin and look at its image. Since G is an isometry, the image of this under the derivative of G will be an orthonormal frame at this point, right?
Yes.
So in fact, G is identified with what's called the orthonormal frame bundle of the manifold M. Well, I'm taking orientation preserving, so it should be positively oriented orthonormal frames. Okay, so this is the orthonormal frame bundle. So this is a fiber bundle over M. Okay, this is a fiber bundle over M. All right, where the fiber above a point P is the set of orthonormal frames at P. All right. So the fiber, the set of orthonormal frames is identified with, well, not okay. Well, actually, no. So I'm sorry. G embeds into the orthonormal frame bundle. For real hyperbolic space, it's equal to the orthonormal frame bundle. In general, G embeds into the orthonormal frame bundle. Sorry. Yeah, this is correct. Yeah. So G embeds into this orthonormal frame bundle. And this Iwasawa decomposition, basically what it's saying is, you see, what you can do is the following. So you have the origin, you fix a geodesic passing through the origin. Okay, so you look at its backward endpoint, you look at the horospheres with this center at infinity. Okay. And now if I want to show that G is equal to KAN, right? Then what are my elements KAN? K is going to be the stabilizer of the origin. Okay. So these will be rotations around the origin, and A will be the translation along this geodesic, and N will be the translations along the horospheres, right? So now what I can do is, if I want to show that G is equal to KAN, I just have to show that any frame at any point, I can move to a fixed frame to this frame at the origin, right? So how do I do that? First, I apply an element of N to move this point onto this geodesic, all right? Along this horosphere, I apply an element of N, you see, to move it here. So I get some frame here. Okay. Right. Now,
Right.
I apply an element of A. Okay. So I apply some element A that moves along the geodesic. So now my point has been moved to the origin. So I can move any point to the origin by applying N and then A, right? Okay. So
Yes.
now I get some frame at the origin. And now I have some frame at the origin. Now I just apply an element of K to move this frame to this frame. Okay. Is it clear?
Yes.
Yes.
So this is geometrically, this is the Iwasawa decomposition. Okay. So G must be equal to Kn. Is it clear?
So this Kn decomposition only works for positively oriented isomer, or does it work for any isomer?
Well, then your K will just become larger. That's all.
Yes, just we are the orientation is coming into
You
play
just,
in case of K only. Right?
you just need to add in one reflection. That's all. That's all. It's as the
Right.
orientation preserving is just index 2 subgroup of the full isometry group.
Right.
Right?
Right.
So you just add one element. That's it. You just
Okay.
add one reflection. So that's just yeah. The K will be index 2 inside the bigger K, which is the full K. You understand?
Yes.
It's
Yes.
like SON
Right.
inside SON
Uh-huh.
inside ON, just index 2. That's all.
Right.
You just add one reflection. It's just SON inside ON. You just add a reflection. That's it.
Right.
So that's not a big deal. Yeah, that's not a big deal. Is this all
Sir,
right?
and
Yeah.
and you said that this frame bundle is equal to the hyperbolic.
No, that's only true. No, that's only true for real hyperbolic space.
Why
For,
is that? Why?
Yeah. So see, the thing is, for real hyperbolic space, K is as large as possible. K is equal to the full SON. Okay. So if M equal to HN, in this case, K is equal to SON, which is as large as possible. Okay. But in general, K is just a subgroup of SON. Okay.
Okay.
It is not equal to all of SON. Right. So for example, if you take M equal to complex hyperbolic space, in this case, K is equal to SUN, which you think of as a subgroup of SO2N. Right, here the dimension is 2N, right, for complex hyperbolic space.
Yes, sir.
Okay, so here you would look at you would not look at all frames, right? You would look at yeah. You would not look at all frames. You would have to look at complex frames in the sense, in this case, the frames you would look at would be of the form E1, J, E1 up to, and then E2, J, E2, where J is multiplication by I. It's a complex manifold, right? So you have a multiplication by I on the tangent spaces. You would look at frames of this type. Do you understand?
Yes.
So these would be preserved by SUN because the elements of SUN, these are complex linear. So do you understand?
Yes.
Yes, so we preserve the complex structure.
They preserve the complex structure. Yeah, they preserve the complex structure. So that's what would happen. Okay. So you would look at these special frames. Yeah. So you wouldn't look at all frames. So you'll get some frame bundle. Instead of the full frame bundle, you'll get some smaller frame bundle. Do you understand?
Yes.
Yes, sir.
Okay, depending on how large K is, you'll get a smaller frame bundle. That's it. So yeah. But either way, this argument for the Iwasawa decomposition, this still works. I mean, this is fine. Okay. This picture is, I mean, this picture is the Iwasawa decomposition basically. So okay. All right, and yeah. So okay, yeah. So let me just say a little bit about this. So suppose add I of W is minus W, then the subgroup GT e to the TW. This gets conjugated to its inverse, right? So now, if I want to classify this GT, then I use the classification of isometries. Okay. So, so I have GT equal to e to the TW and IGT I inverse equal to G minus T because add I of W is minus W. So then I look at cases. So well, okay. So note, then what happens? So then I sends the fixed points of GT to fixed points of the conjugate, I GT I inverse, right?
Yes.
Which is the same as fixed points of G minus T. And G minus T is just the inverse of GT. It has the same fixed points as GT. Okay. So that means I preserves the set of fixed points of GT, right?
Yes.
Okay. So so this implies that GT cannot be parabolic because I has no fixed points on the boundary. Okay. Right? Because fixed points of I intersect boundary M is empty. Right? If GT was parabolic, then it would have a unique fixed point on the boundary. That fixed point would have to be fixed by I, right?
Yes, sir. Yes.
But I on the boundary is just the antipodal map, right? It's just the antipodal map of the sphere Sn minus 1. So it has no fixed points on the boundary. So therefore, the GT cannot be parabolic. Okay. So then there are two cases. One, if GT is elliptic, okay. So then, so say oh, actually, yeah. So say yeah, so say P is a fixed point of GT inside M. Okay, let me end this meeting and start another one. We're less than a minute, so we'll start another meeting. Okay, so okay, wait. So let me just fix this. So actually, no, we don't have to look at cases. So what we have is that yeah. Okay. So what we have is that, see, if I take this G minus T to the other side, I inverse is equal to I. So what I have is that IGT, this is equal to identity, right?
Yes.
Okay. So that means that, I mean, IGT squared is identity. So that means that IGT is elliptic, right?
Yes.
Because the parabolic and hyperbolic are of infinite order. Okay. So the only finite order elements, possible finite order elements, isometries are all elliptic. Okay. So IGT is elliptic. Okay. So suppose P is a fixed point of IGT inside M. Okay. Then look at T, which is the derivative of this IGT at the point P. So this goes from TPM to itself, right? Because P is a fixed point. Okay. So then T is an orthogonal linear map of the tangent space, and T squared is identity, right? Okay. So that means the eigenvalues of T are all +1 or -1, right?
Yes.
But as little t tends to 0 here, right? GT tends to identity. So IGT converges to I, right? So T tends to minus to the derivative of I at yeah, so this has to tend to minus identity, right? As t tends to 0, t has to tend to minus identity, because GT tends to identity, and the derivative of I at the fixed point then will become minus identity, right?
Yes, sir.
So that means actually for t small, for little t small, capital T has to equal minus identity, right? All the eigenvalues have to equal -1. If it's close to minus identity and it's orthogonal, its square is identity. So all the eigenvalues are either +1s or -1s. There can't be any +1 eigenvalues, right?
Yes.
Is this clear? Yes?
Yes, sir.
Okay. So, so this implies that T is equal to minus identity for little t small. Okay. And so then what happens? Right. So then that means that wait, okay, I'm getting a bit of a contradiction here, aren't I? No. Wait. Well, I just wanted to rule out the case that GT is elliptic. So one second. So then T squared is identity, T is minus identity. Okay, yeah, right. So, okay. Yeah, so then IGT must be a Cartan involution, right? It would be right. Okay, yeah. So then IGT would be I sub P, right? For T small. Is this clear? Yeah.
Yes.
This P depends on T. P depends on T. P belongs to fixed point of IGT. Okay. Fine. So I've got this. So yeah, so we're almost done. I just want to say that GT is hyperbolic and then I'll be done. So yeah, right. So right. So if this is my origin and this is P, okay, then what is the product of these two Cartan involutions? Well, I take the geodesic from the origin to P, right? Then as we saw, the product of these two Cartan involutions will be a hyperbolic translation along this geodesic, right?
Yes.
Yes. So, I mean, if I take, let's say, the this point here, then it will go here, and then it will go here, right? I mean, GT is going to be I0 IP. I is equal to I0. So is this clear, right? So this will be GT. So GT will become hyperbolic, and hyperbolic along a translation along a geodesic passing through the origin, right? So when I differentiate with respect to t equal to 0, then what I'll get is that so I mean so GT will become a K conjugate of AT. Okay. Right, where K is basically the rotation which moves the AT geodesic. This is AT dot O, and K moves this geodesic to this geodesic. Is this clear? Yeah. And so when I differentiate, then I'll get that W is equal to add K of H. Okay. So therefore, finally, what I get is that the kernel of add I plus identity is equal to add K H, where K belongs to well, span of this. Well, no. Well, okay, so there'll be some constant, A lambda T lambda. So lambda. Okay. So lambda at KH. K belongs to K. Lambda belongs to R. Okay. This will be the kernel of add I plus identity. I think this is correct.
So this is a geometric picture of the Cartan decomposition.
No. It's just a no. The geometric picture of the Cartan decomposition is just the polar coordinates. That's all. It's just the polar coordinates.
Yeah.
This is I wanted to identify this -1 eigenspace of add I, right? That's all.
Yes.
So earlier I said it was just the span of H. It's not just the span of H. It's the span of add K into H, where K belongs to capital K.
Yeah. I mean, the way we saw the USR decomposition as the composition of isometries, we can again do the same here with moving to the geodesic by rotation, then translating through the geodesic and again rotating back to the other point, KK. And this.
Yeah, that gives the Cartan decomposition.
Right.
Correct.
Okay.
That gives the Cartan decomposition. You take a frame at this point, you rotate it by a K element, then you translate it by an A element, and then you rotate it again to get the a fixed frame at the origin.
Right.
That gives you the Cartan decomposition. Yeah.
Okay.
That gives you the Cartan. Okay, fine. So the last thing I want to say about symmetric spaces, which is what Utsa was asking me, is how do you get this sub-Riemannian structure of the Heisenberg group from these roots? Okay, and the Riemannian structure on the horospheres. So the sub-Riemannian structure of N. So this is connected to the roots. So what happens is you foliate your space by horospheres. Okay. And then, so these are codimension 1 submanifolds. So if I take if I take the geodesics passing through this point at infinity, these will be orthogonal to the horospheres. Okay. All right, so I have these two orthogonal foliations. One is a foliation by horospheres, and the other is a foliation by geodesics. All right. Yes, and so these give sort of Cartesian coordinates. Okay, so if I fix the origin and I fix the horosphere, let me call it, say, I shouldn't call it H. I don't know. Let me call it sigma. Okay. This is the horosphere passing through the origin. Okay. So this is the N orbit of the origin. Okay. So then I have a natural map. You see, I have these. So let me call this point on the boundary xi. Okay. So I have a Boseman function B xi associated to this boundary point from M to R. Okay. And these geodesics are what? These are just the integral curves of the gradient flow of the Boseman function, right? Right. Remember, the gradient vector field of the Boseman function was just the outward unit normal to the horospheres, right?
Yes, yes.
Okay, so these geodesics, these are given by the flow of the gradient flow of the Boseman function. So let phi t be the gradient flow of the Boseman function. Okay, so this xi is equal to the fixed point set of the group N. Okay, the fixed point set of N is equal to this singleton xi in the boundary of N. Okay. All right. And phi t is the gradient flow. So the gradient flow moves along these geodesics. So this gives me coordinates, Cartesian coordinates on the whole space. I have a map, let me call it capital phi, from sigma cross R to my symmetric space N. What is the map? I take a point, say, P on this horosphere, and then I flow it by time t, right? So that will give me all points in the symmetric space, right? You take any point, I can get it by starting from this horosphere and flowing towards it, right? Do you understand?
Yes.
So the map is P comma T goes to phi T of P. Okay, so this is a diffeomorphism. Okay, this is a diffeomorphism. So that means M is identified with sigma cross R, the horosphere cross R, and the horosphere is identified with the N, the group N, right? So this you can identify with NA, okay? So this is the NA picture of the symmetric space, all right?
Yes.
Okay, now what you can do is you can take the metric on M and pull back to sigma cross R, okay? So you look at, so if G naught is equal to the metric on M, okay, then you pull back, you look at phi star G naught. This is a Riemannian metric on sigma cross R. Now the point is, because these horospheres are perpendicular to these geodesics, these integral curves, if I look at the in sigma cross R, right? If I look at how should I put it? So
This is the slices, sigma cross singleton T kind of things.
yeah. No, wait. No, wait. Let me finish. What I'm saying is, if I look at, let's say, the tangent space to sigma, okay, and the tangent space to the geodesics, okay, so the tangent space to sigma will be spanned by the ni's, all right, and the tangent space to this will be spanned by del t to the geodesic. Then these two are orthogonal, right, for the pullback metric, because they're orthogonal in M. Okay, so that means when I write out the metric as a 2 tensor, I won't get any cross terms. Okay, so so this will be basically some summation
In terms of metrics, it will be block diagram.
one second. Let me just think for a second. 1 second. Yeah, it will be in fact block diagonal. So if I take the roots, I goes from 1 to n minus 1. Yeah, then what will happen is, in fact, this will be of the form e to the alpha it d ni squared plus dt squared. Okay, this will be the form of the metric, where these dni's, these are the dual one forms to the vector fields ni's, del ni. You see the ni's are coordinates. So these are, yeah, these are just the derivatives of those coordinates. Okay, I have coordinates n1 to n, ni's on this sigma, right? So, and when I pull back, what will happen is, see the yeah, so why do I get this factor e to the alpha it? That's because when I flow along these geodesics, right, what happens to my vector at the origin? I saw that moving along this, right, it gives me a Jacobi field, which is basically a parallel field times e to the alpha I t, right? Yes,
Yes, sir.
we saw that last time. So that means when I pull back, I'll get this e to the alpha I t into dni squared, or there'll be 2 alpha I t because I'm looking at the square. So e to the 2 alpha I t dni squared, and then I'll get a plus dt squared. There won't be any cross terms dni dt, okay, because the del ni direction and the del t direction are orthogonal, okay?
Yes, sir.
So this is what is called, so this part is just a metric on sigma times a function of t, and this part is a dt squared. This is what's called a warped product metric, okay? This is called a warped product metric. Okay, so now what is happening to, so you see, this is the metric basically. If I restrict to a level set here, sigma sub t, which is sigma cross t, singleton t. Okay, so that corresponds to a horosphere at height t here. Okay, this will be, this is your this will be, say, sigma sub t. Okay, so what is happening? Certain directions are getting expanded by factors e to the 2 alpha I t, right? Or e to the alpha I t. The lengths are getting expanded by e to the alpha I t, right? Okay, so in the horosphere, basically there are different orthogonal directions. Here's n1, here's n2. So the n1 direction is growing like e to the alpha 1 t. The n2 direction is growing like e to the alpha 2 t, all right? And what you want is, see, the sigma t's in a sense are converging to the boundary, right? Which you're identifying with n. Okay, this boundary m, this you're identifying, this boundary m minus xi, this you're identifying with n. Okay, so in a sense, the sigma t's are converging to n. Okay, so these metrics, you want to get a limit of these metrics to get a metric on n. The problem is the alpha i's could be different, right? In that case, you don't get a metric on n because some directions will blow up to infinity, while if I rescale, so I take the smallest. So let me say alpha 1 is the smallest, okay? And alpha n minus 1 is the largest. So what I can do is, so this thing, let me call this ht. This is a metric on sigma t, okay? So I can look at ht divided by e to the 2 alpha 1 t, okay? So then the first one direction, the n1, the directions for which grow like alpha 1 e to the alpha 1 t, those stay finite, but the other directions go to infinity. So in the limit, this converges to h, which is what's called a sub-Riemannian metric. On n, okay, which is you think of as the limit of the sigma t's. Does this make sense?
So
this
ht is the usual metric at t level, right?
Yeah, this metric, this is ht, this e to the summation to
okay.
the 2i alpha t dni squared. So what happens, I divide by e to the 2 alpha 1 t. Okay, so look, some of the alpha i's are equal. All right, alpha 1. What happens actually for a symmetric space is that n has a decomposition as a center, direct sum, a non-central part. Okay, it's two-step nilpotent. So here you have one root. There's actually just two roots, right? I think, yeah. So for rank 1, I mean, so this is yeah. Is that right, Rudra? There's just one root alpha 1 for this and another root alpha 2 for this, right?
Yeah,
That's correct, right? Yeah.
yeah.
So so when I divide by e to the alpha 1 t, this part is going to become this part is going to stay finite, but this Riemannian metric will go to infinity on these directions, in the v direction, the non-central direction. Okay, so you get what is called a sub-Riemannian metric. That means it's a Riemannian metric on a distribution in the tangent space. It's not defined on the full tangent space. It's just defined on a distribution. Okay, because on the vectors which are transverse to the distribution, you think of it as being infinity in those directions. Okay, so this is how you get a sub-Riemannian metric. Okay, because it comes from the fact that the metrics on the horospheres are are diverging at different rates. Okay, they're diverging at different rates. So if I take the smallest growth, then I rescale so that that stays finite. Then the other directions, they go to infinity, right? Okay. So this is a Riemannian metric on a distribution. Okay, this is a metric. So this is not defined on the full tangent space. This is defined on a distribution. Say script H, which is a distribution inside the tangent bundle of n. Okay.
And the dimension of the subspace is exactly n-1.
No. No. No, well, yeah. n-2, n-2.
Okay.
Wait, no. No, it's not. In general, no. No, it's going to be the dimension of the central part, right?
What is that's what I'm asking.
Well, yeah, I'm not sure actually which one is larger, Rudra, the central or the non-central? Which of these two is the larger one? The central is larger, is it?
No, non-central will be large, right?
Non-central is larger, I see. Okay.
Yeah, I think so. Yeah.
Okay, that doesn't quite match.
Yeah, here in symmetric space, you are getting a particular type n, right?
Yes, a particular type n, right, correct. Yeah.
Heisenberg type.
Heisenberg type, yeah.
Yeah, for them, the center is small.
The center has smaller dilation.
Right.
For rank 1, what will be the sum?
No, that depends on the rank 1. There are different types of rank 1, like complex
Okay.
item, like quaternion.
I mean,
It's not a
since the important part is Heisenberg, the non-central part is of even dimension. That's all I think we can say.
No. What I'm asking is, look, you have AT which is acting on N, right? By anisotropic dilations. Yes.
Yes.
So what are the eigenvalues of AT?
So you're asking like which part the dilation is the scale was.
Yeah. So on one of these, it will be like e to the t, and on the other, it will be like e to the 2t, right? So which one is which? I don't remember which is which. So
I think the non-central part dimension is much bigger.
no, I'm not asking about the dimension. I'm asking about the dilation. What is the dilation coefficient of the non-central and the central part, right? The roots. what are the roots in the central part and the roots in the
So the
non-central?
let me just, the same, it's like square, the square of the, what I'm saying is that in the central part, the dilation will be more.
Central part, the dilation will be more, right?
Like, you can say that in the non-central part, if it is square here, the central part is like that square, yeah.
Yeah, so in the central part, if the dilation is e to the 2t, then in the non-central, the dilation is e to the t, right?
So the central part, it will go to infinity, that's what you're saying, yeah. If it is, yeah.
Yeah. So the central part will go to infinity. Exactly. The non-central part will stay finite. Exactly.
Yes.
So that's what happens for CHN. For CHN, right? I mean, the N is the Heisenberg group, which is C N minus 1 semi-direct R, right? This R, this is the central part. And this Cn minus 1, this is the non-central part. So
Yes.
you get a sub-Riemannian metric on this Cn minus 1. The sub-Riemannian metric is defined here, okay, on the non-central part. Okay, so this is a distribution of codimension 1, right, in the Heisenberg group, the Cn minus 1. And this gives you what's called a contact distribution. So you get a contact distribution and you get a sub-Riemannian metric there. And then you have this Chow's theorem that because it's a contact distribution, any 2 points in the Heisenberg group can be joined by a horizontal curve. That means a curve which is everywhere tangent to the distribution. And then you have your sub-Riemannian metric on the distribution. So you can integrate and find lengths of horizontal curves. And then you define this, your Carnot-Carathéodory metric is the infimum of the lengths of horizontal curves. So that's how you get the metric structure on the Heisenberg group. Okay, so
Yes.
yeah. Okay, so I just wanted to end with that. The point is this sub-Riemannian structure is coming from the different growth rates of the horospheres. Do you understand? So in this direction, horospheres will grow. I mean, you see these Jacobi fields, these will grow like e to the alpha 1t. Right. In another direction, they'll grow like e to the alpha 2t. Okay, they'll grow faster. Okay, so the horospheres, they're not growing at the same rate in all directions.
In case of the hyperbolic space, we get that it's all the roots are same, so we get
Exactly, yeah. So in case of hyperbolic space, you get a Riemannian structure on the boundary. N is just equal to Rn minus 1 with the usual Euclidean metric. The this sub-Riemannian metric is actually just a Riemannian metric in this case for the real hyperbolic space.
yes.
Yeah, but you get this sub-Riemannian structure because these Jacobi fields grow at different rates in the different directions. Okay, so that's because the roots are different. So the roots give the growth of these Jacobi fields. So, okay. Does this make some sense?
Yes, yes.
Yeah, so I don't know if this is really, well, I think in Gromov's book, he writes something like this. So you can look at Gromov's book, but Gromov's book is a very big book. So I don't know which part of it you should look at really. I've read a little bit of it, and he does talk about the limits of, sub-Riemannian spaces coming as limits of Riemannian spaces. So that's the idea. They come as limit of Riemannian metrics, these sub-Riemannian metrics. Yeah. So, I mean, the same thing you should be able to do for any NA group. So you look at the same picture, you have the horospheres inside the NA group, right? Yeah. And I mean, you should get a sub-Riemannian structure on N from from the growth rates of the horospheres inside NA.
Yeah, I mean, like we can't speak of roots there, but like the different growth rates, that's all we can say.
Yeah, I mean, the roots are basically the eigenvalues of AT acting on N, right?
Right.
That's all. You have your anisotropic dilation. It's just the roots are just e to the roots are just the AT, the eigenvalues of AT acting on N.
Right, the growth rate of the horospheres. Yes, in
Right.
different directions. Yeah. Okay.
Those are the roots. So anyway, if you're more interested, you should look at Gromov's book. But I mean, it's a big book, so well, you can look at the introduction.
Title of the book, sir?
Oh, it's Subramanian spaces, metric and Subramanian. I'll send you the title of the book. Yeah, I'll send you the title.
Oh, sir.
Yeah. Something Subramanian geometry and Riemannian geometry, something like that. Yeah, I've forgotten the exact title, but it's a long, like a 400-page book. So, I mean, yeah. So you can read some
Is
of
the
it.
metric geometry book you are saying?
That one. Yes. What's the title, Rudrada? I forget the title. Metric geometry for Riemannian and
Yeah,
Subriemannian.
Riemannian and Subriemannian metric, I think.
Right. Metric geometry for Riemannian and Subriemannian spaces. That's the book. Yeah. That book, yeah. So, but I mean, Gromov's book is even more sketchy. There are no proofs. I mean, hardly. I mean, so yeah. So, but anyway, it's worth having a look just to get some ideas. It's worth having a look. So, okay. So I think this is enough about symmetric spaces. So we'll get back to general manifolds. Let me start another session. Okay. We're out of time for this one. Just wait a second for Rudrada's audio is still connecting. So yeah, connected. Okay. All right. So, okay. So now let me come back to general manifolds. Okay. So just any Riemannian manifolds, no curvature assumption, nothing. Okay. And we can finally start talking about the Laplacian. Okay. So the first thing that will be important for us to define is what's called the divergence of a vector field, right? So this you would have seen in Rn, the divergence of a vector field, but we can define the divergence of a vector field on any Riemannian manifold. Okay. So M is a Riemannian manifold. Okay. So let me first suppose that M is oriented. Okay. So then we know that we have a volume form, right? So we have a volume form, dvol, which is an n form on M. Okay. Then we can define for a vector field X on M, we know that if I look at the Lie derivative of the volume form, right, then this is again going to be an n form, right? So any n form is going to be a function times the volume form, right? Because the volume form is everywhere non-zero. So any n form is a function times the volume form, right? Yes.
Yes, sir.
So then we define the divergence of x to be this function. So div x, this is defined to be this function f. Okay, so this is a smooth function on M. Okay. So thus, the divergence is defined by requiring that the Lie derivative of the volume form is equal to the divergence, it's a function, the divergence of x times the volume form. Okay. All right. Is this all right? Yes.
Yes.
Now, here we assume that M was oriented so that we have a global volume form. But orientation is not really an issue here. In the general case, if M is not orientable, I mean, not necessarily orientable, then what we can do is we can just work with local volume forms, right? I mean, every point has a neighborhood, which is a ball, which is orientable, right? So on a ball, we will have a volume form, right? So, well, there are two choices of orientation on the ball. So those will give two volume forms, but those two volume forms will just be negatives of each other, right? Yes?
Yes.
So, I mean, so then we define the divergence using the local volume forms. Okay, and we still have, so if M is not necessarily orientable, we still have local volume forms, say d vol u on balls u in M, and then you define divergence of x by the equality Lx d vol u equal to div x d vol sub u. Okay. So this is well defined, independent of the choice of local volume form, because I mean, there are just two local volume forms on this ball u, right? There's d vol u and minus d vol u. If I choose minus d vol u, then I just put a minus sign here and a minus sign here. This divergence stays the same, right? Is that clear?
Yes.
Okay, so this is well defined, independent of the choice of local volume form. All right. Is this clear?
Yes.
Okay. Yes, Orkojit, is this okay?
Yes.
All right. If I use the other volume form, that's minus d vol u. So Lx of minus d vol u will be what? It will be minus Lx of d vol u. That will be minus div x into d vol u. That will be div x into minus d vol u, right?
Yes. Right. Right. Yes.
So you get the same function div x,
Hmm.
no matter
Right.
use devolve or minus devolve, right? So this is independent of the choice of local volume form. All right. Okay. Okay. So this is how the divergence of a vector field is defined. And note that the divergence is 0 if and only if the Lie derivative of the volume form is 0, if and only if what? The flow of x is volume preserving. Right? Okay, so the divergence measures how far the flow of x is how far it is from being volume preserving. All right?
Yes, right.
Okay. Yes, Utshab, is this all right?
Yes, sir.
Okay, so now let's come to the notes. So, okay. So note that by Cartan's formula, this div x into dvol, let's say a local volume form, dvol u, this is equal to Lx dvol u, right, by definition. And Lx dvol u, Lx, the Lie derivative, we saw this is equal to dix plus ixd, right? That is Cartan's formula, right? We proved Cartan's formula in the beginning of the course. So this second term here is going to vanish, right? Because d of dvol is a n plus 1 form, which is 0 because the dimension of m is n, right?
Yes.
So the second,
Yes, sir.
so this is just equal to d of ix dvol u. All right. Okay. So we have this formula for using this formula, we'll be able to calculate explicitly the divergence. All right. This div x into dvol is dix dvol. Okay. So a main tool in the study of the Laplacian also is what's called the divergence theorem. Okay. So let me come to the statement and then we'll do the proof. So suppose M is orientable and let D be a domain. So that means an open connected subset of M with smooth boundary del D. And suppose that D closure is compact. Okay. So then if I look at D closure, that's D union boundary D. This is a compact orientable manifold with boundary del D, right? And so for any point P in del D, we can identify the tangent space to the boundary with an n-1 dimensional subspace of TPM. And as before, we can define outward pointing vectors V in TPM minus TP boundary D, right? It's a manifold with boundary. Remember, we defined what were outward pointing vectors, right? That means if you take a chart near P, that maps a neighborhood in D closure. It maps it to a neighborhood of a point on the boundary of the upper half space, right? And then an outward pointing vector was a vector which whose image under the derivative of the chart points out of the upper half space. It points into the lower half space, right? Yes?
Yes, sir.
Okay, so we defined what was an outward pointing vector earlier for manifolds with boundary. And now, since we have a Riemannian manifold, there's going to be, in fact, a unique outward pointing vector, which is of norm 1 and which is orthogonal to the tangent space to the boundary, right? This tangent space to the boundary is of dimension n-1 sitting inside the tangent space to M. So its orthogonal complement has dimension 1, right? So if I restrict to vectors of norm 1 in the orthogonal complement, there are just going to be 2 vectors. So only one of those will be outward pointing, right? One will point inwards, one will point outwards. Okay. So therefore, there is a unique outward normal vector, outward unit normal at each point of the boundary of D. Okay. So we get a vector field N from boundary D to the tangent bundle of M, which it's not hard to show. This is a smooth vector field, okay, on boundary D. All right. So this is the outward unit normal. Is this okay?
Yes,
Yes.
sir.
Okay. So now we can state the divergence theorem. So let M be an oriented Riemannian manifold, and let D in M be a domain with smooth boundary, del D, such that D bar is compact, D closure is compact. Then for any vector field X on M, we have the integral over D of the divergence of X, D vol, is equal to the integral over boundary D of the inner product of X with the outward normal, ds. Okay, so N here is the outward unit normal to boundary D, and ds, this is the volume form of boundary D. Okay, so remember that since D is oriented, boundary D has an induced orientation, right? And so boundary D is a oriented Riemannian manifold, so it has a volume form. Okay, so ds is the volume form of the boundary of D. Is this all right?
Yes.
Okay. So, I mean, geometrically, what is this saying? I mean, you might have, this is taught in, I mean, I remember learning this, I mean, not learning, I mean, using this in class 12 physics, right? You must have seen this in physics when you're calculating flux through a surface and so on. You have a domain D. You have your vector field inside. Right? Didn't you study this Gauss theorem, Gauss's divergence theorem in physics?
Yes, yes.
In class 12 physics, you must have had it. Well, at least I remember having it. Anyway, so so the divergence at each point, in physics terms, it measures how much is flowing out. If you think of, say, the vector field, the flow of the vector field as the flow of, whatever, electrons or electric field or something, right? So then the divergence in physical terms is a measure of how much is flowing out at each point. Okay, so suppose it's fluid or fluid flow, how much fluid is flowing out at each point, and then the integral of the divergence over the boundary, over the domain, this should give you the net amount which is flowing out of the whole domain. So how do you get the amount which is flowing out of the whole domain? You look at the vector field on the boundary and take the component which is perpendicular to the boundary, right? So
Yes.
that will give you the amount which is flowing outside. So that is exactly this integral xn ds. Okay, boundary D. Okay. So this is Gauss's divergence theorem. Okay. Okay. So let's prove this. So it will follow actually just from Stokes' theorem after a little calculation. So first of all, by Stokes' theorem, the integral over D of div x d vol, this div x d vol we've seen by Cartan's formula. This is the same as D of Ix d vol, right? The integral over D. So by Stokes' theorem, this is the integral over boundary D of Ix dvol, right? Yeah. So
Yes.
by Stokes, this integral becomes an integral over the boundary of this Ix dvol. Now Ix dvol, this is an n-1 form on this n-1 dimensional manifold boundary D, right? So all we have to show is that Ix dvol restricted to boundary D is equal to X inner product N times ds. Then we're done, right? So that's what we're going to show. Okay. So let P be a point in boundary D, and let E1 to En-1 be a positively oriented orthonormal basis of the tangent space to boundary D. Okay. So positively oriented means, from the definition of the orientation on boundary D, this means that if I take n of P together with E1 to En-1, this will be a positively oriented orthonormal basis of TPM, right? This is how the orientation on boundary D was defined, if you remember. Yes?
Yes.
Yes?
Yes.
Okay. Okay. So now we have a basis of TPM. So my vector X at P, I can write with respect to this. This is an orthonormal basis. So it's going to be given by a linear combination X inner product N times N plus some summation alpha I EI, right? Okay. So now I know that if I take Ix dvol, this is an n-1 form. So if I restrict it to the tangent space of boundary D, then it becomes an n-1 form on an n-1 dimensional vector space. Therefore, it is a multiple of the volume form DSP, right?
Yes.
So it is going to be lambda times DSP for some lambda. We just have to compute what is this lambda, right? So let me write lambda as lambda times DSP of E1 to En-1. Yeah, because ds applied to E1 to En-1 is 1, right? By definition of the volume form of the boundary, right? This is a positively oriented orthonormal basis of tangent space to the boundary, and ds is the volume form of the boundary. So ds acting on this basis gives you 1, right? So I can write lambda as lambda times ds of this, but lambda times ds is my Ix dvol. So this becomes Ix dvol acting on E1 to En-1. Now, what is the definition of Ix dvol? That means you put an X in the first position, right? So this becomes dvol of X together with E1 to En-1, right? Okay. Now I write X as this linear combination of N and the basis vectors EI. Okay, so this becomes dvol of inner product Xn times N plus summation alpha I EI, and then E1 to En-1. Now I use the multilinearity. So I expand out this. So the first term will become inner product Xn into dvol of N E1 to En-1. But N together with E1 to En-1, this is a positively oriented orthonormal basis of TPM. So dvol acting on this will give you 1, right? By definition of the volume form. Okay. And what happens to the other terms? Well, the other terms give me summation I goes from 1 to N-1, alpha I dvol, and then what do I get? EI, and then E1 up to En-1, right? But this means that EI will occur twice here, right? And since dvol is an alternating form, that means that this will become 0, right? If EI occurs twice, this will become 0. Yes?
Yes, sir. Yes.
Okay. So this second term, all of these vanished. So then all that remains is just X inner product N. So that means this coefficient lambda is equal to X inner product N. And therefore, Ix dvol is equal to X inner product N into ds, okay, when restricted to the tangent space to the boundary. And so therefore, the divergence theorem follows. Okay. Is this clear?
Yes.
Yes.
Yeah, this is fine. Okay. Okay, so that proves the divergence theorem. All right. Yeah, okay. Now we'll develop some further properties of the divergence. So let some formulas for divergence of a product and so on. So let X be a smooth vector field and phi a smooth function. Okay. And suppose dvol is a local volume form. All right. So we want to compute the divergence of phi times X. Okay. So let's do that. So by definition, divergence of phi X into dvol, this is equal to d of I sub phi X dvol, right? But now in this interior contraction with phi X, this means you just put a phi X in the first spot, right? But by multilinearity, the phi will come out. So this is the same thing as phi times Ix dvol, right? Okay. And now by Leibniz rule for the exterior derivative d, this will be d phi wedge Ix dvol plus phi d of Ix dvol, right? Yes?
Yes.
Yes, right.
Okay. So now let's look at this first term, d phi wedge Ix dvol. So this is an n form, right? So therefore it is equal to f times dvol for some function f. Okay. So we want to compute what is this coefficient f. So we work in the same way like we did earlier. So f I write as f into dvol of E1 to En, where EI is a positively oriented orthonormal basis of TPM. Okay. So then f into dvol, this is d phi wedge Ix dvol. So this becomes d phi wedge Ix dvol applied to E1 to En. Okay. Now, if d phi p is equal to 0, then of course d phi wedge Ix dvol at p is equal to 0. And so then f of p will be 0, right? So we can assume that d phi at p is non-zero. So in that case, grad phi at p is also non-zero, right? So now we're going to choose this orthonormal basis EI in a special way. So we let the first vector E1 be grad phi divided by norm grad phi. Okay, so we can do this because we're assuming grad phi is non-zero, right? Then we extend this E1 to a positively oriented orthonormal basis, E1, E2 up to En, okay? So my first vector E1 is grad phi divided by norm grad phi. And the other vectors E2 to En, these are therefore going to be orthogonal to grad phi. So that means that if I is in between 2 and n, then d phi p of EI, that by definition is inner product grad phi p with EI, that is going to be 0, right? Yes? Okay.
Yes.
So
Yes,
we've chosen our orthonormal basis in such a way that d phi, it vanishes on E2 up to En. Okay. Therefore, when we look at this wedge product, okay. So wedge product means what? You take the tensor product and then you apply the alt map, right? Then you apply the alt map. The alt map means you have to apply, take permutations of the EIs and then apply the tensor product to them, right? But if I permute the EIs, any permutation which sends a E2 or an E3 or an En into the first spot is going to give me 0 because d phi of E2, E3 up to En is 0, right? Yes?
Yes.
So I won't, so those permutations will vanish. So I'll only get the permutations which fix E1, right?
right.
So therefore, this wedge product applied to E1 to En, this will just be, it will split as a product. D phi E1 into Ix dvol of E2 to En. All right?
Right.
Okay. And now I can compute this. D phi of E1 is what? This is grad phi inner product with E1. E1 is grad phi divided by norm grad phi. And then I have dvol so Ix dvol of E2 to En. So this means dvol of X and then E2 to En. So X is summation I goes from 1 to N. X inner product EI into EI, right? It's an orthonormal basis. And then E2 to En, okay? So now what happens to this first term? This will give me grad phi squared divided by norm grad phi. So that gives me just norm grad phi into, now here again, if I is not equal to 1, then EI will be repeated twice here, right? So I'll get 0. Yes?
Right.
So the only term which will remain here is when I is equal to 1. So then I'll get X E1 and then dvol of E1 to En, that is equal to 1. So, so then what will I get? I'll just get norm grad phi into X into E1. And norm grad phi into E1 is equal to grad phi, right? By definition of E1. So finally, this will just boil down to X inner product grad phi. All right. Okay. Is this clear?
Yes.
Yes, sir.
Okay, so therefore my coefficient F here, where I was writing this d phi wedge Ix dvol as F times dvol, this F turns out to be just inner product of X with grad phi. Okay, so therefore I get d phi wedge Ix dvol equal to inner product grad phi with X into dvol. And therefore I get that divergence of phi X into dvol is equal to inner product grad phi X dvol plus what was the second term? The second term was phi times d of Ix dvol. D of Ix dvol, by definition, this is div X into dvol, right?
Right.
So I'll get the second term is phi div X dvol. Okay. So so therefore, I mean, I can, in a sense, cancel the dvol from both sides. And so I get that the divergence of phi times X is inner product grad phi with X plus phi times div X. All right.
Yes.
Is this okay? So this is a sort of Leibniz rule for the divergence, right? This is a sort of Leibniz rule for the divergence. Okay. So as a corollary, if M is an oriented Riemannian manifold, then if we take any vector field X on M and any CC infinity function phi, so any smooth with compact support function phi, then the integral over M of phi times div X dvol, this is equal to minus the integral over M of inner product grad phi with X dvol. So this formula you should think of as an integration by parts formula. Okay, this is an integration. In Rn, this would just be integration by parts. If M is equal to Rn and you take the usual definition of the divergence, you can just prove this by integrating by parts. Do you see that?
Yes.
Okay, in Rn, this is just integration by parts. So anyway, in a manifold, this formula is true too. So what happens? So this integral of phi div X dvol, we first write this as the integral over some domain D, which contains the support of phi, okay? And so such that D closure is compact. So this is integral over D phi div X dvol. And phi div X from this formula is equal to divergence of phi X minus inner product grad phi X. So this becomes integral over D of divergence phi X dvol minus integral over D grad phi inner product grad phi X dvol. And this first term vanishes by the divergence theorem because this becomes an integral of phi X inner product N over the boundary of D, and phi is 0 on the boundary of D. Okay, that's how we chose the domain D. So this term vanishes, and so you are just left with this term. And so this is minus the inner product of grad phi with X dvol. Is this okay?
Yes.
Yes, sir.
Okay, now let's compute the divergence in local coordinates to finish for today. I think that should be enough. And we'll see that it's a first order differential operator, just like in Rn, all right? So suppose X is a vector field and we take local coordinates phi equal to x1 to xn. And let's write X as summation X super I into del del xi, okay, with respect to the basis del del xi, okay, locally. And let dvol be a local volume form. So this local volume form, we know we can write it as square root of the determinant of G times dx1 wedge dxn, right? Where G is the matrix of the Riemannian metric. Yeah, this we've already seen, right? Yes?
Yes, sir.
Okay. So then we have to compute the divergence. So that we know, basically we have to compute d of Ix dvol. So let's first compute Ix dvol, right? So Ix dvol will be then square root determinant G into Ix of dx1 wedge dxn. So that's square root determinant G. So Ix of this dx1 wedge dxn, this is an n-1 form, right? So remember we had a this is an n-1 form. So this is going to be a linear combination of the basis forms of the basis for the n-1 forms. Those will be the forms d1 wedge dx j-1, wedge dx j plus 1, wedge dxn, right? Basically with dx j omitted, right? And what will the coefficient of this basis form be? It will be Ix dx1 dxn acting on the subset of the basis del del x1, del del xj minus 1, del del xj plus 1 up to del del xn, right? Yes?
Yes, sir.
Okay. So Ix dx1 wedge dxn acting on these basis vectors, that's the same as dx1 wedge dxn acting on x comma these vectors. Okay. And now x, when I write x as summation xi del del xi, what will happen? I'll get a summation xi del del xi here. So unless I is equal to j, if I is not equal to j, then del del xi will occur twice here, right? Yes?
Yes.
If I
Yes,
is not
sir.
equal to del del xi will occur twice, so that will vanish. So the only term which will remain is when I is equal to j. So then I'll just get an xj del del xj here. Okay, so that xj will come out. So I'll get xj dx1 wedge dxn acting on del del xj, del del x1 up to del del xj minus 1, del del xj plus 1, del del xn. And this thing I can permute j minus 1 times to bring the del del xj into the jth position, right? Just get 1. So that will give me a factor of -1 to the j minus 1. Okay. So therefore, I'll get finally that Ix dvol is equal to square root determinant G into sum over j -1 to the j minus 1 xj dx1 wedge dxn with dxj omitted. Okay. So this is the n-1 form Ix dvol. Is this all right?
Right.
Yes.
Now we calculate the divergence. So div x dvol is d of Ix dvol. So I have to take d of this. So that will be a sum over j -1 to the j minus 1 d of square root determinant G xj dx1 to dxn with dxj omitted. So by definition of the exterior derivative, this will be d of this function wedge the rest. Okay, And d of this function is sum over I del del xi of square root determinant g xj dxi, right? Okay. And now I have a sum over I here. But again, if I is not equal to j, then this dxi will be repeated twice here, right? So I'll get a dxi wedge dxi, which is 0, right? So the only terms which will remain is when I is equal to j. So then I'll just get del del xj of this, and I'll get a dxj wedge this, and then I do a permutation to move the dxj into the jth spot. So that will give me another factor of -1 to the j minus 1. And so finally I'll get sum over j del del xj of square root determinant g xj into dx1 wedge dxn. Okay. And this dx1 wedge dxn I write as 1 over square root determinant g into dvol. Okay. So finally I've got d of so div x dvol is equal to this function dvol, and so therefore div x is equal to this function. Okay. So we get a first order differential operator. Is this all right? Okay.
Yes, sir.
Yes.
Okay. So let me stop here. Okay. Let me stop. We're out of time. Let me stop. Okay. So see you next week.